Okay, so welcome everyone to this time is the 8th lecture already of Introduction to Quantum Optics. And let me just start reminding you what we have seen already. So let me just go to the beginning of the chapter. So I remind you that what we were doing in this chapter was analyzing the interaction between light and matter. And in this chapter, we really consider the full interaction between quantized electromagnetic field and matter. And what we saw was a few general ideas initially. First, we saw that in principle, what one needs to use in order to describe the interaction between light and matter, it's relativistic quantum electrodynamics. But this is a bit of an overkill at optical frequencies because we don't have particle production. So we don't change the fundamental constituents of the matter that we are interacting with. And therefore, in principle, we can just stick with a non-relativistic quantization. But even this non-relativistic quantization doesn't need to be very rigorous in the sense that we use the Maxwell equations for the electromagnetic field, but using the matter degrees of freedom as sources. And for the matter, we use a multi-particle Schrodinger equation, and we couple it to the vector potential of the electromagnetic field through minimal coupling and so on. We can do something even simpler, at least, whenever the interaction can be treated as a perturbation, okay? And whenever matter admits a model in terms of some kind of fundamental electric dipoles, okay? And then the picture that we have of matter in this scenario and in quantum optics in general, it's something of the following type, that we have a material that it's overall neutral, and at every point you can think of it as a neutral material, but you know that deep down, this neutral material is built from electrically charged constituents, and therefore, that maybe they are bound, and this is why you see it as neutral. But therefore, when you apply an electric field from outside, light or any other thing, then what happens is that these tiny dipoles get displaced, okay? The field tries to pull apart negative and positive charges. And this is essentially, to first order, the most important effect that the electromagnetic field has on our fundamental constituents of matter. And then this means that we can essentially describe our system, our matter, from the point of view of the interaction with light, just as some kind of electric dipole moment per unit volume that we call electric polarization density, and we call it just this P. Or if it's not a continuous material, so if it's not, let's say we don't have a bulk material, we don't have a solid or whatever, we have really some kind of fixed dipoles, then this is what we get. We have each dipole at some specific position, and that's the electric polarization density in that case. So then what I try to argue is that whenever you can do this kind of model, then the system or the interaction is described by a very simple Hamiltonian in which you just have the separate Hamiltonians that describe light and matter that we have already studied, and then the interaction between light and matter as a separate perturbation, okay? So it's a small Hamiltonian compared to the other two. And in particular, this perturbation, given that we have dipoles and we are applying an electric field, it's just the interaction of dipoles with an electric field, which is E times P, okay? And we also saw, sorry, that we can define some even more simple level of approximation, which is what we call semi-classical approximation. And in quantum optics, whenever someone says semi-classical, usually what we refer is to the situation in which we have quantized matter, but we don't quantize the electromagnetic field. And therefore matter interacts through the dipole moment per unit volume with an electric field that is just a classical field that you can find from the Maxwell equations that you can solve with coupling to matter or without. I mean, this is different depending on the level of approximation that you want to do. And we will see today one example of this semi-classical theory that we have actually just studied in the previous chapter with the semi-classical Rabi Hamiltonian. Okay, but then what we started doing, because this is very generic, we started looking at one specific matter system, which is the simplest kind of matter system that exists, which is just a single atom, and in particular, a single valence electron atom. So this is essentially the perfect example of a single dipole. So in which we have a positive charge and a negative charge that are bounded, and they are separated by some distance r. And therefore, this gives us just a dipole, which is proportional to the atomic relative coordinate that we already discussed in the chapter of matter. And then what we did was something that it's called, I think I didn't mention it, but this is called cavity quantum electrodynamics, which is taking an atom and putting it inside an optical cavity and let it interact with the modes of the cavity. And therefore, in that case, what we get is that we take the atom, we put it inside the cavity at some position, okay? Of course, the electric polarization density, it's given by this simple expression because we have just one dipole at position R0 inside the cavity. And therefore, the interaction Hamiltonian will simply be the product between the electric field inside the cavity at position Z0, which is the position of the atom, times the relative coordinate of the atom, okay? And we also discussed that this has the implicit assumption that the electric field is constant at atomic scales, okay? So we can really take it at one specific position, which is, let's say, the position of the center of mass of the atom, and that's enough. And that we justify because the atom's size is way smaller than the wavelength of light, which is the distance over which the electric field of light changes. Okay, then what we saw is that this generic Hamiltonian of one atom interacting with the electric field of a cavity can be further simplified if we make the assumption that there is only one transition, one atomic transition that is resonant with only one optical mode in the cavity, okay, of frequency omega. Then in those conditions, we can forget about all modes but one, and therefore the electric field inside the cavity for that specific mode can be written in this way, which is just proportional to the annihilation and creation operators. And of course, the relative coordinate of the atom can be written just as a Pauli X operator, okay? Then if this is the situation, then the light-matter interaction simplifies to this relatively simple Hamiltonian in which we have only the free motion of our harmonic oscillator, our optical mode, then the free motion of the atom with sigma z, and then we have an interaction of the type A minus A dagger, so the P quadrature interacting with sigma x. And this model, it's called the quantum Rabi model, okay? So remember, always remember that this parameter G, okay, which is given in terms of microscopic details of the system, we are always working in the situation in which this G is much smaller than the typical frequencies or transition frequencies of light and matter, okay? That's what we mean when we say that we take as a perturbation the light-matter interaction. And this is the situation that you will find very naturally in all experiments around the world. And actually, if you want to go beyond that limit, if you want G to reach close to the optical or atomic transitions, then you really have to work extremely hard in the lab, okay? So usually this is what you get with G much smaller than this. And so what we saw is that even this Hamiltonian that looks relatively simple because it's just a Hamiltonian for a single harmonic oscillator interacting with a single two-level system, even that doesn't have a simple analytic solution. So it has an analytic solution since a few years ago, maybe already 10 or something more. You have the references in the notes if you are curious about it, but it's still a very complicated solution. So, and we can use the fact that the interaction is a perturbation to make one more approximation. That is what we have seen already in the previous chapter that we call the rotating wave approximation. And in particular, what we saw is that we can essentially prove that out of all the terms that are contained in this interaction, okay, in particular, this interaction contains this kind of four distinct terms, in which you can either absorb a photon to create an atomic excitation or emit a photon by de-exciting the atom, or you have other processes in which you simultaneously absorb a photon and bring the atom down, or the weirdest one, let's say, is the same kind of term, but even weirder to think about it, that the atom suddenly, spontaneously get excited and at the same time emits a photon, which, let's say, from the point of view of energy conservation that we have in mind, doesn't make any sense. And we saw that indeed, we can make this doesn't have any sense a bit more formal by invoking the rotating wave approximation. And the way to do the rotating wave approximation is always the same. So I just explained you in a bit of detail. We always take the part of the Hamiltonian that we think defines the energy scales. So let's say the part of the Hamiltonian that dominates the full Hamiltonian. We take it and then we move to a picture, okay, in which we discount that Hamiltonian. I remind you that we saw as well how to change between pictures. And in particular, we saw that you can always define an arbitrary unitary transformation that can be time dependent, arbitrary wherever you want. And then you can move to a picture defined by that unitary transformation in which there is a new state, okay, that is just the state that you had transformed by the unitary, that will evolve according to a new Hamiltonian in that picture. And that new Hamiltonian looks relatively simple because it's just the transformed Hamiltonian through the unitary that you have defined, minus some term that when the unitary, you take it just as the exponential of a time-independent Hamiltonian, then this is just the Hamiltonian that you are putting in the unitary. So in other words, you have that the interaction Hamiltonian is just the transformed Hamiltonian minus the transformation Hamiltonian, okay? Then if we apply this to our light matter interaction with a single atom, then what we get is that if you take this as the Hamiltonian, as the basic Hamiltonian, which is just the light matter Hamiltonian, okay, the light and matter Hamiltonians, only this part, then we know how all the operators of the system transform through this unitary. They just acquire these rotating phases, okay, at the optical or atomic frequencies, depending whether it's an optical or an atomic operator. And then the interaction Hamiltonian can be written in this simple form in which we just take the interaction part and we transform it, okay? If we do that and we use this, then what we get is that we have two distinct types of terms in the Hamiltonian. The first one, which we call HR or H rotating, that's where the R comes from, is a term that you see that oscillates slowly because omega minus epsilon can be 0 or close to 0. On the other hand, the other term, which we call H non-rotating and R, this one rotates very fast because it's always rotating at frequencies omega plus epsilon, which cannot be close to 0. And that's way faster than the interaction G, as we have mentioned. Then this automatically means that these terms in here are negligible within the rotating wave approximation, okay? Then we will neglect them. And again, this can also be justified once you know the energy scales. This can be justified just by energy conservation arguments, okay? So once you know that creating a photon and creating an atom, an atomic excitation, both are processes that require an energy, a given energy, okay, from the energy scales that we have, then you know that this process will only happen whenever the interaction is providing that order of magnitude of the energy, which is not the case in our case because G is just a perturbation. Okay, then we can neglect this, and with this, we will start the lecture of today. So let's study what happens when we use the rotating wave approximation on the quantum Rabi Hamiltonian. And what we get, it's something like this. So within the rotating wave, approximation, we have that the Hamiltonian can be approximated by h bar omega a dagger a plus h bar epsilon over 2 sigma z. So this is just the light and atomic Hamiltonians. And now we have the interaction that we have approximated just by what we call the rotating term, or rotating wave approximation term, in which we can annihilate a photon or absorb a photon and create an atomic excitation, or emit a photon by de-exciting the atom, okay? And this Hamiltonian here has a very special name. This Hamiltonian is called the Jaynes-Cummings Hamiltonian, so JC, the JC model. And let me write down the name. So this is the Jaynes-Cummings Hamiltonian. Okay. And as we are going to see, so in contrast to the Rabi Hamiltonian that is very difficult to diagonalize, this Hamiltonian here is actually easily diagonalizable. Okay. So this is the first thing that I want to do. So in essence, what we are going to do for the rest of the, at least the first part of the lecture, is we are going to study phenomena or effects, quantum mechanical, quantum optical effects that occur in this system using this Hamiltonian, okay? And for that, it's always interesting to know the eigenstates and the eigenvalues of the Hamiltonian. Once you know that, then you can calculate anything you want. So then for the first part, what we are going to do is precisely diagonalizing this Hamiltonian, okay? And this brings me to what are called dressed states. So the eigenstates of this Hamiltonian, we usually call them dressed states. And let's talk about them and let's find them. So the first thing that we need is to define always the Hilbert space of the system. But in our case, the Hilbert space of the system, H, is very simple. It's just the tensor product of the light's Hilbert space, which is just a single mode, and therefore is just one harmonic oscillator, tensor product with the atomic Hamiltonian, which we are assuming it's just a two-level system and therefore a two-dimensional Hilbert space. And of course, as we have discussed before, either in the exercises or at the beginning of the course, this means that this Hilbert space can be spanned by a basis that in this case will contain the following type of states. You can have n excitations in the optical mode and the atom in the ground state. And I remind you that when I write that, what I mean is the Fock state and tensor product with the ground state of the atom. Or you can have n excitations in the field and one excitation in the atom, so it's in the excited state. And this n goes from 0 to infinity in units of 1, okay? So once we have a basis of the Hilbert space, then we can think about representing the Hamiltonian and diagonalizing it and so on. And in particular, this is very simple for the Jaynes-Cummings because of the following property. So the Jaynes-Cummings Hamiltonian, okay, it can connect only pairs of basis states which are specifically n excitations in the field and the atom in the ground state. It can connect it only with n-1 excitations in the field and the atom in the excited state, okay? This is very simple to understand because just imagine that you have this situation, okay? So you have the atom in the ground state and you have n photons in the field. Then if you come to the Hamiltonian, you see that, of course, these operators here do not change either the number of optical or atomic excitations because they are eigenstates of this. And therefore, we have only the interaction that can connect different basis states. And in particular, you see that this operator here will always create an excitation only by removing a photon, okay, or de-exciting by emitting a photon. But this means that if you want to go from the ground state to anywhere, you have to jump to the excited state by removing one photon. But once you are in here, if you apply the Hamiltonian will only be able to go down to the ground state by absorbing a photon. So you come back to the original state, okay? So this means that effectively, this is just a two-dimensional problem. Okay, so you only need to consider two states of your basis states, the only two that are connected, by pairs. We will formalize it now better. But essentially, you see that once you are in one of these states, you can only connect to another one. So effectively, it's a two-dimensional problem. So let's make this more formal, and let's do it exactly in a rigorous quantum mechanical way. So this can be formalized by defining an operator. So let me just define the following operator. I call it E. Don't confuse with the electric field. We are not talking about the electric field anymore in this chapter, which is simply this Hamiltonian here. So just what is this Hamiltonian doing? This is counting the number of excitations. And the way to see this is very simple because, well, you know that A dagger A counts the number of photons, and this operator here is nothing but the excited state projector, okay? And therefore, what you are asking is whether the atom is in the excited state or not, okay? So then this counts the number of excitations, and let me formalize it even more. So let me formalize it by just telling you that actually the basis states, these states in here, are eigenstates of this operator with the following eigenvalues. So first of all, let me write down how is the action of this operator on the very basic what we expect to be the ground state of the system, of having no photons and the atom in the ground state. So if you apply this operator to this state, you get 0 because you have 0 photons, okay? And the excited state projector acting on the ground state, it's 0. On the other hand, if we apply this operator to the state with n excitations in the field, n photons, and the atom in the ground state, you will get n times the same, okay? And when you apply it, and this is the interesting point, when you apply it to a state that has n-1 photons, but it has the atom excited, then you also get eigenvalue n, okay? Because now you will get n-1 photons from the Fock, from the number operator, but now that you are in the excited state, you will get a 1 also from the excited state projector. So in total, you have n-1 plus 1. And therefore, this is also an eigenstate. So, and what's important is that then you see that actually this operator E has doubly degenerate eigenvalues. Okay? So then this operator, as I said, it counts the total number of excitations, okay? Without distinguishing whether the excitations are in the field or in the atom, okay? But this means that for a given number of excitations, you have a doubly degenerate space, except for when you have 0 excitations, in which then there is only one state that satisfies that, okay? So then what's interesting is that the Hamiltonian commutes with this operator. So the Jaynes-Cummings Hamiltonian commutes with this operator E. And therefore, this automatically implies several things. First of all, they have common eigenstates, okay? Because they commute, so they can be diagonalized simultaneously. And this automatically means that when you apply the Jaynes-Cummings Hamiltonian onto the 0G state, okay, which is an eigenstate that is unique in the sense that it has a unique eigenvalue for operator E, then this has to be an eigenstate of the Hamiltonian, and in particular, you see that is an eigenstate with eigenvalue minus h bar epsilon over 2. Okay, and this is the absolute ground state of the system. So this is the minimal energy that you can have in the system, which is very natural because I remind you that we are setting the energy origin, we are setting it in between the excited state and the ground state of the atom, which means that if you have 0 photons and you have the atom in the ground state, then you should be half an atomic transition below the origin of energy, which is precisely this term in here, okay? And on the other hand, the excited states of the Hamiltonian, okay, must lie in the degenerate subspaces. Okay, so in particular, this means that because we have doubly degenerate subspaces, then you know that the any linear combination of these two states, Ng and n-1 E, is an eigenstate with the same eigenvalue of E, and one of those or two of those linear combinations should be eigenstates as well of the Hamiltonian, okay? And going even more rigorous into it, so just in case you think, oh, but you have to kind of have a very, profound or funny idea in order to realize this, that you connect only to states and whatever. That's true, but what you can do always is just represent the Hamiltonian. So if we take a representation of the Hamiltonian, for which you don't need to think, you just know the basis, and then you apply the representation theory, and we represent it in this basis. So it's the basis that we know, but we need to order the eigenvectors. And for example, let me order them in this kind of natural way, in which we just increase the number of excitations one by one. So we have something like this. Okay. So this is 0 excitations. These two give you 1 total excitation. These two give you 2 total excitations, and so on. Then if you do that, the Hamiltonian, it's just easily written, or the representation of the Hamiltonian is just easily written as what we call a direct sum. I don't know if you are familiar with this, but I explain you in 1 millisecond what this means. This means that if you find the matrix form of this Hamiltonian, it has a box structure. So it will have in the kind of diagonal, it has boxes, or it has matrices, okay, that are non-zero, but everywhere else you will get zeros, okay? So essentially, this is telling you that so the direct sum means exactly this, that you just you kind of add the Hamiltonians or the matrices that you have in the direct sum, okay? You add them in the diagonal one after another, and then you get this funny box structure. And whenever your Hamiltonian has a box structure, then you know that you only need to diagonalize the boxes, because there is no coupling in between the different boxes or the different subspaces associated to every box. In particular, for this Hamiltonian, for the Jaynes-Cummings, you can check very easily, so please do it. And of course, you have it in the notes very carefully, but you can check very easily that this first box, H0, which is nothing but the matrix element of the Hamiltonian in this absolute ground state. This is just minus h bar epsilon over 2. And then for the other boxes, so the other HNs, this is a 2 by 2 matrix that contains the matrix elements associated to the 2 states that we have for a given total excitation number, which, let me write explicitly. Oops, I forgot to put Jaynes-Cummings in there. So it will be exactly this kind of term. And then here, the diagonal one. Okay. And in particular, the concrete expression of these matrix elements in the Jaynes-Cummings Hamiltonian is just something like this. Let me just write them down. This is an epsilon. Then we get here n minus 1 omega plus epsilon half, and then I square root of ng minus I square root of ng. So this is a a very simple matrix because it's just a 2 by 2 matrix and it is Hermitian. Okay. And therefore we know how to diagonalize it. So as I say, if you just take the basis and you do a representation of the of the Hamiltonian in this basis, you will find automatically this box structure in which the first box is actually 1 by 1, so it's just a number, and the rest of the boxes are 2 by 2, and in particular given by these matrices here that are 2 by 2 Hermitian matrices. So then once we have this, we know how to diagonalize the Hamiltonian because this is just a 2 by 2 Hermitian matrix. In the notes you have, if you haven't read them, go because you have them, how to diagonalize a 2 by 2 Hermitian matrix in general, any 2 by 2 Hermitian matrix, okay? But I'm sure that you already know how to do it, but just in case I put it there. And for this specific case, it gives something like this. So the eigenvectors associated to these matrices, once we go back to the Hilbert space and so on. So let me just first give them a name. So we are going to call these eigenstates of these subspaces. We will call them psi plus and minus for the subspace with n total excitations. The energies, we will call them the same. So energy plus minus for the n total excitation subspace. And this is what we are looking for. So the eigenvectors. Then if you just diagonalize this matrix, as I am saying, this matrix in here, then you automatically get the following spectrum that I am going to show. Of course, here I am talking about n larger or equal than 1. So because for n equals 0, we already know the eigenstate because we have a 1 by 1 matrix. So we have a single vector, 0g. And then what we get is the following. So regarding the energies, so the energies will be given by this expression here, which we will interpret in a second. Where this omega n is given by this thing here, delta square plus 4 n g square, where delta, it's something that we have already found. It's what we call the detuning. The detuning between the optical field and the atomic transition. So the optical frequency and the atomic transition, which is just omega minus epsilon. And therefore, if you remember what we saw in the previous chapter of the quantum theory of matter, what we saw is that we can define something called the Rabi frequency that exactly has this kind of expression, like the detuning square plus some kind of interaction or some kind of perturbation to the free Hamiltonian, which has some expression. And therefore, we call this the quantum Rabi Hamiltonian, frequency. Okay, so we will see actually frequencies because we have a different frequency for each number of excitations n. Okay, so we will in a second understand that this quantity is very important in this context and why it is so important. But okay, for now it's just a parameter that kind of parameterizes what is the energy eigenvalues. And then concerning the eigenvectors, we get the following eigenvectors. It's also interesting to write them down. So the eigenvector plus associated to the subspace with n excitations, you can write it just as a superposition of these states n, g. So the atomic excitation is, or the atom is in the ground state. And so this is a theta, and the atom is in the excited state. So n minus 1 excited. So in both cases, of course, the psi minus and the psi plus. But then the mixing angle, so you see that there is a single parameter, a single angle that determines what is the ratio of ground state and excited state of the atom that you get. So where the excitations are more located, or in the atom or in the field, this is given by a very simple expression, which is just 1/2 of the argument of this complex number. Okay, this is a complex number that it's always between 0 and pi over 2. Because, so just take a look in here. So this is positive. So the imaginary part is positive by definition, okay? Because g is positive, square root of n is positive, and then g has a plus. And then the detuning delta can be positive or negative. You can be at resonance with the atom, or slightly above the atomic frequency, or slightly below. And therefore, what you get is a real part that goes from positive to negative. So this means that this number, or this argument, is between 0 and pi, okay? And then you have here a 1/2, and therefore the overall angle is between 0 and pi over 2, which makes perfect sense because this means that this angle can be either the cosine equal to 1 and then the sine equal to 0, or the cosine equal to 0 and the sine equal to 1. Okay, so you go between the two extremes of the excitation being completely in the field and the excitation being completely in the atom. Okay, so okay, this looks a little bit dry because it's very mathematical. So let me show you exactly how the spectrum looks in a way that will make perfect visual sense, which is this one in here. So I hope you can see it properly. And let me just explain what we have here. So forget for a second about this yellow part, okay? So don't think about this yellow part. In these gray parts in here, so what I am plotting here is just the energy, okay? And then I am plotting here the energy levels of your system. So in the absence of coupling, so if we take the Jaynes-Cummings Hamiltonian, but we don't have any coupling, so we set G to 0, then the energies are very clear. We have either the atom is excited or not, and we have the harmonic ladder, so the uniform spectrum associated to A dagger A, okay? So this means that if we plot the eigenenergy, okay, what we will get is that when the atom is in the ground state, we have the possibility of having 0 photons or 1 photon and therefore an energy h bar omega, or 2 h bar omega, 3 h bar omega, etc. So we have one harmonic ladder. Or we have the atom in the excited state, in which case the energy is already epsilon for 0 photons. Okay, so we have already the energy of the atomic excitation, which is not exactly the same as omega. Okay, you see that it's slightly below in this picture. And then you can add to that 1 photon or 2 photons, so you get h bar omega plus epsilon, 2 h bar omega plus epsilon, etc. So this is the energy spectrum when there is no coupling. What is the coupling doing? The coupling is doing the following. First of all, even with coupling, the energy of the ground state doesn't change, and the ground state itself is still the same. So then this is what I represent in the yellow region, okay? This is the spectrum associated to the Jaynes-Cummings model with G different than 0. And what we get is exactly this. What we get is the ground state, it's still the ground state, but then the first two excited states will be linear combinations of these two states with one excitation either in the field or in the atom, okay? And what's interesting is that the splitting between these two energies, or the energies of these two states, it's precisely given by this quantum Rabi frequency, okay, ω1. Then if you go to the second, to the subspace with two excitations that can be either two in the field or one in the atom and one in the field, then you will mix. So the eigenstates are mixing these two eigenstates, free eigenstates, and the energy splitting is ω2. And you see that in the next states, then you are mixing the eigenstates with 3 total excitations and with an energy splitting of ω3. So this is essentially the spectrum of this Hamiltonian, okay? This Hamiltonian has a very simple spectrum of kind of doublets splitted by a quantum Rabi frequency of the corresponding subspace. So, but I want to show you even one more thing to make this more clear. But before I do that, let me just give you one useful set of relations that we will use in a second regarding this angle theta. So it's very easy to prove that this angle theta also satisfies this kind of relations in which I can write down the cosine of theta and the sine of theta in very simple terms, just as the detuning divided by the Rabi frequency or the coupling part of the Rabi frequency, so this part in here, so the square root of that, divided the Rabi frequency, okay? So this is just some useful expression that we will use later. So is it clear, the spectrum of this Hamiltonian? So I know that you have to digest it and you have to do it yourself to convince yourself, but at least I hope that you understand the structure, okay? That's the only thing I care about right now. And then you can prove this carefully with the notes, okay? But then there is another quantity that is very interesting, which is the following. So these are energies. So these are eigenenergies of the system. But in general, in experiments, it's very, let's say it's very difficult to measure energies. Usually what you measure are energy transitions. So the energy of the transitions, okay? So you can probe the system with some kind of external field in which you try to induce transitions between the ground state and, for example, the first pair of excited states. And this is what I am going to show now. So if we calculate how are the energy transitions as a function of the detuning, we get an effect that maybe you have seen in quantum mechanics already, because this is very generic in quantum mechanics, but it's very important, and therefore I want to discuss it, which is called avoided crossing. So let me explain you in detail what this means. It's very easy to understand. So it's this plot in here. Okay, so let me just show you what I am plotting here. Here I am plotting the transition frequency, okay, between the ground state and the first pair of excited states. So either the plus or the minus. So it's exactly these transitions here, either this one or this one, okay? As a function of the frequency of the cavity. So imagine that you do an experiment in which you put the atom inside the cavity, and now you start changing the frequency of the cavity, like moving the mirror, for example. And for each frequency, someone has a question. One microphone is open. I don't see the question, so maybe mute it. Okay. So then, so as I was saying, imagine the experiment in which we have the atom inside the cavity, we change the frequency of the cavity, and then we probe the transition between the first or the two first transitions, okay? And then what we get is something that looks like this. And let me just explain you carefully. So imagine first that there is no coupling, absolutely no coupling, okay? If there is no coupling, this means that we get two transitions. So either the ground state is connected to the first excited state where the excitation is optical, and this goes as the frequency, okay? And therefore, this means that we will get this gray line in here, in which if you calculate what is the energy transition, so E plus minus E0, as a function of omega, you just get something linear in omega, okay? Or you can couple the ground state to the other excited state in which we have an atomic excitation, but this atomic excitation is at epsilon, is at the atomic frequency. It doesn't depend on the cavity frequency, and therefore it's just constant, okay? So you can change the cavity frequency as much as you want, but that transition will always be at epsilon, okay? So then, as you see, we have a crossing. So we have a point when the atomic frequency is the same as the optical frequency, as the cavity frequency, then we have that the transitions are the same, and otherwise they have some kind of difference. But we have a crossing. Then what is the effect of adding an interaction between the atom and the cavity field? Because we are mixing eigenstates of the Hamiltonian, what happens is that we get what is called an avoided crossing. So when the frequency of light is very far off resonance of the atomic frequency, okay, we know that this means that there is effectively no coupling, and that's what we see, that the transitions approach the transitions that that appear when there is no coupling. But as you get into resonance, so as the cavity becomes resonant with the atomic frequency, you see that you modify a lot the optical, sorry, the energy transitions. And in particular, you don't let them cross, and you get a splitting that is maximum at the atomic frequency, and it's equal to 2 times the coupling. So this is very, very important for many reasons. First of all, because it allows you to check experimentally in which regime you are working. So if you do an experiment and you don't see the avoided crossing, so you see that they cross, you know that there is no coupling, that you are not inducing any coupling between your optical field and your atomic transition. And if you see a splitting, then that allows you to calculate exactly what is the value of the coupling, okay? And also, it allows you to evaluate what is the atomic frequency, because you can change the cavity frequency. That's something that you know. You just have to change the length of the cavity, for example, okay? And then by changing the length of the cavity, you can see when you get the maximum splitting. And when you get the maximum splitting, you know that you have the frequency of the atomic transition. This is a way of measuring optically atomic transitions or atomic energy transitions. Okay, so essentially, I believe that this is all I want to tell you about the spectrum of this Hamiltonian. Okay. just think a little bit about it. We will do a break now, as we discussed. We will do 2 breaks today. So welcome back. So we have just seen the spectrum of the Hamiltonian, of the Jaynes-Cummings Hamiltonian. And now that we know the eigenvectors and eigenvalues, we can start thinking about interesting dynamical situations. And this brings me to what we call quantum Rabi oscillations. And let's study what we mean by this. Maybe I remind you very quickly what was the Rabi oscillations. We have it here. So when we first talk about Rabi oscillations was in the context of the semi-classical Rabi Hamiltonian, which is just a Hamiltonian for a single atom, in which, apart from the free term that is sigma set, we add a term that goes as sigma x multiplied by a term that rotates at some frequency that is close to the one of that oscillates at a frequency that it's close to the one of the atom. And in that context, what we saw is that if we start from the atom in the ground state, okay, which in the Bloch space it meant this vector, then what we have is that we can track what is the population in the excited state as a function of time. And what we saw is that we have some kind of periodic behavior in which, when we are at resonance, so resonance between the periodic forcing and the atomic transition, we manage to transfer the full population from the ground state to the excited state. But if we have some detuning, then we have an imperfect population transfer. But in any case, we see these kind of oscillations between the atom being in the ground state completely and partially to the ground, to the excited state, and then back to the ground and back to the excited, and so on. And in particular, the frequency of those oscillations are what we call the Rabi frequency. Okay, so back to this quantum model, or this model in which the frequency, the field is completely quantized. Now what we ask is the following question. So we let the state of the atom be the ground state initially. So we have a ground state atom initially. And this essentially means that our starting state at time 0, it's going to be essentially the following superposition. So we allow the field to be in any kind of superposition, okay, of Fock states. So it's the most general pure state, only pure states, but the most general pure one. But the atom is in the ground state, okay, that's fixed. Now, we want to see how this state evolves under the action of the Jaynes-Cummings Hamiltonian. And in order to do this, as you have already, or many of you did naturally in the exercises, the best thing is to write down the original state, so this initial state, in the basis of the Hamiltonian, okay? And this is very easy to do because we know the eigenstates of the Hamiltonian, so they are here. They are very simply connected. So let's say the state NG, okay? It's very easy to connect with them because we can just invert this relation to write down the following. So let me write down these relations. So the state NG, so when the atom is in the ground state, this is equal to cosine of theta n, and then the plus state, and then a plus sine of theta, and then the minus state. Okay, and of course you can do the same with the n-1 e state that we will use in a second as well. And now you get the orthogonal combination. Okay, so then this is the relation between the basis states, the basis states that we chose at the beginning, and the eigenstates of the Hamiltonian. And then using this, we can rewrite this initial state just in the following form. So we will have this plus then the sum from 1 to infinity of Cn cosine theta n psi plus n plus sine theta n psi minus n. Okay, so of course, because 0g is already an eigenstate of the Hamiltonian, we simply pulled it apart of the sum, and then the other terms in the sum and g, they are just equal to this combination here. Okay, then if we now allow the atom cavity system to evolve freely under the Hamiltonian, that is the Jaynes-Cummings Hamiltonian. So this is what we call unsupervised evolution. For this Jaynes-Cummings Hamiltonian, the unsupervised evolution postulate, it tells us that the Hamiltonian, the system will evolve according to just applying the time evolution operator onto the initial state. Okay, and this automatically means that because these states here are eigenstates of this Hamiltonian with energies E plus minus, okay, and then you see that E plus and E minus have this common thing in here, proportional to h bar omega, and then the difference is only this plus minus in here, with its plus minus the Rabi frequency divided by 2. Then we can write this in this very simple way. So we get, so first, the part of the ground state, it just remains in the following way. So we will have minus, so it's plus, so it's I epsilon t over 2. And then we will have the action of the unitary evolution operator, time evolution operator, onto the eigenstates of the Hamiltonian. Sorry, let me write it down in this way. First, we will have the part that is common to the plus and the minus energies. And then we will have the parts that are different for each of them. In particular, we get this. And let me make a bit more space. Okay, so essentially, because these are eigenstates of the Hamiltonian, then the evolved state is just adding the exponential of minus I energy times the time to each of the corresponding eigenvectors. And therefore, this means that for this particular Hamiltonian, now we can evaluate how any observable will evolve in time, and therefore any experimental observation, how it will evolve in time, or how it will depend on time. So in particular, let me focus on one, that is the atomic excited state population. which we already studied, as I have shown in the previous chapter, for the semi-classical Rabi Hamiltonian. But now we will do for the full quantized model. And this is what we call PE, so the probability of being in the excited state. And this is nothing but the expectation value of the projector in the excited state. But of course, now we have two Hilbert spaces, the one of the atom and the one of the cavity mode. And this means that what we are asking is the projector in the excited state, and we don't care about what happens to the field. So then we just take the identity for the field. And then we need to evaluate the expectation value of this operator here. Okay, it's the excited state projector for whatever happens in the field. We don't care. Then if, so this expression here, it's very easy to compute because we can rewrite the identity as a sum over Fock state projectors, and then we get this kind of expression for that operator, whose expectation value we are interested in. So it will be n times E. Okay, and this is simply equal to the sum from 0 to infinity of the projections of all the states in which the atom is in the excited state, the projections of the evolved state square. So let me maybe give you a bit more space. Okay. So essentially, we could have thought about this from the beginning, but it's good to really go through the quantum mechanical definitions, because then you don't make mistakes. But at the end of the day, we simply ask, what is the probability that the atom is excited when the cavity has n photons? Okay, and then we just sum over all the probabilities, okay, over all the photon numbers. And that's the probability of the atom being excited for anything happens in the field. But we know very well what is this projector here, because we know that if we just take this, so this probability amplitude, okay, the projection of the state onto an E, we simply have to go to the state. This is our state. And then we project this state onto NE, sorry, yeah, NE. But then this is the ground state in the atom, so this goes away. And then the only thing that is left is this projections of the states psi and minus onto NE. And that's very easy to calculate, that we know. So let me just write down the expression. So we will have sum from 1 to infinity of Cm E minus I m minus 1/2 omega t. And then we start with the projections. So first, we have the projection of the psi plus state onto NE, and then we have the projection of the psi minus state onto NE. And these projections we know as well. That's why I wrote the connections between the states. Because, well, let me go to the states, maybe better. So you see that when you just take the state psi plus and you project with NE, what you get is a delta function of the corresponding Fock numbers and this minus I sine factor. And for the psi minus, you will get the I cosine factor and the same kind of delta function. So in particular, this is just to say that this factor here is equal to minus I sine of theta m, and then delta n plus 1 m, and here is the same, but with the cosine. Okay, and therefore, at the end of the day, if we just use the delta functions in here and we take into account that we get, in both terms, we get a sine times cosine and sine times cosine, that is common factor, and then we get this exponential of minus and this exponential of plus. This will give us a sine, okay? Because we have a minus sign in here. So at the end, if you simplify this expression, you will find very easily that this is just equal to Cn plus 1. Then this phase factor, and then we get the sine of 2 theta n plus 1 and the sign that oscillates in time. Okay, so very simple, but again, please do it yourself as well. Do this calculation carefully, and you will see that this probability amplitude is just equal to this factor here. And this is a very interesting structure because this oscillates in time with the Rabi frequency, the quantum Rabi frequency, and it has an amplitude or a value that is set by this mixing angle. So whenever the mixing angle is large, then we get a large value. Whenever it's small, then we get a small value. Then if we use this, the final expression for the probability of the atom to be excited, so the excited state population, this is just equal to the sum from n equals 0 to infinity. So we have it here, remember? So it's just the sum from 1 equals 0 to infinity of this, the square of that. So essentially, this thing here, sine square and sine square and now it's interesting to write it in the following simplified expression. So I will just use two very simple identities that you know very well, which is just that the square of the sine can always be written in terms of the cosine of 2 times the angle. So in particular, this expression here. So for any angle phi, the sine square is 1 minus the cosine of 2 phi divided by 2. And the other expression I will use is one that I told you that would be useful. That is that the sine square of 2 theta n, it's equal to just, so I show you better. It's just equal to the coupling. So 2 square root of ng divided by the Rabi frequency. But the Rabi frequency is this thing in here, which already has this, this numerator in the denominator. So then overall, we can write it, because we have the square, we can write it in this simple way. 1 over 2, and then times 1 plus delta square divided for n g squared. Okay? So you will see in a second why this form is kind of better. But let me write it down and then I discuss it. So we get this numerator and then this in the denominator. Or if you want, Maybe I put the 1/2 outside, and then here I just keep 1 plus delta square divided for n g squared. Okay? Now, this expression is very nice because, first of all, now we see that the oscillation frequency is omega n for each of these terms. Okay? So we have a sum, and I also changed the n index because here we have n plus 1. So instead of 0, I can call it, I can call n plus 1 n, and then we run from 1 to infinity. And then we see that each of these terms is a term that oscillates at the Rabi frequency, at its quantum Rabi frequency, omega n, and it's divided by a factor that depends on a single parameter, which is the detuning of the detuning of the cavity with respect to the atomic transition, normalized to some kind of coupling in the n photon subspace or n excitation subspace. Okay, but essentially we have two important parameters: the Rabi frequency of n and the normalized detuning of n. Okay, so essentially this is the expression that we are going to analyze now, and we are going to understand the physics that can be derived from this expression. And let me start just with two very simple examples. So remember that this expression is completely general in the sense that the field, the cavity field, it's still allowed to be in any pure state, whatever pure state you want. Okay, you start with the cavity in any pure state. Then if we do that, then we get this expression, but now we can particularize to some specific initial states. So let me consider the following examples. So first, I am going to talk about starting with 0 photons in the field. So this means that we really start from the ground state of the system. So no photons, no atomic excitation. And of course, well, this means that Cn is equal to delta n 0, okay? So in the expansion of the field, we only consider n equals 0, and therefore Cn is delta n 0. But what this implies automatically is you see that the probability of being excited starts at n equal 1. So C0 doesn't contribute here. Therefore, this is equal to 0. Okay? But this is, of course, normal. Like this, we have done only to check that the theory that we are using is correct. Because, of course, if we start with no excitations in the field and the atom in the ground state, the atom cannot get excited because it cannot absorb any photons. There are no photons, okay? So then we stay in the ground state. Perfect. So let me then start with something that it's less trivial. In particular, let me start with the atom, sorry, the cavity in a Fock state with n atom, with n photons. Okay, so this is a Fock state. Okay, if we do this, then this means that the coefficients Cn, they are all 0 except for the one of the photon number that we are considering, capital N. And this means that the probability of being excited, the atom being excited, becomes this simple thing here. Okay, but maybe you want to remember how it was with the semi-classical Rabi oscillations, because this is really similar. Let me just remind you. So look, when we were saying that we had a classical field interacting with our atom and we have Rabi oscillations, this is the expression that we got for the excited state probability, okay? And it's exactly 1 minus the cosine of a Rabi frequency divided to 1 plus the detuning square normalized to the Rabi coupling, okay? To the bare Rabi coupling, so to the just to the interaction between the light and the atom. And what did we find now? So now we found something that is essentially the same. It's the same kind of expression, but now the Rabi frequency, so let me just maybe write it down. So this expression is exactly the same as the one with the semi-classical theory, so semi-classical Rabi oscillations. But with an omega that we defined in there, an omega that in this case is 2 square root of n g, okay? And this is why we call this quantum Rabi oscillations. Okay, so we call this quantum Rabi oscillations because in this case we have a quantized electromagnetic field interacting with the atom. And even though we have this quantized situation, if you put the cavity in a Fock state, if you put the field in a Fock state, then you get the same kind of physics as with the semi-classical Rabi model, in the sense that you get these Rabi oscillations of the atomic population, okay? Exactly how we saw in the previous chapter. So these are the two simple examples that I want to discuss. Now we will move to one example that is not trivial. So if you want to ask something about this derivation, please go ahead. Otherwise, we move now to an interesting situation, which is considering a coherent state initially. So coherent light, okay? And we will discuss what happens for coherent light with Rabi oscillations, and then something very important in quantum mechanics, which is called collapses and revivals. So, but perhaps in order to motivate this a bit, let me actually pose a problem, okay, a puzzle that we have found. So perhaps let me just write explicitly that we find ourselves in a peculiar situation. So in a very peculiar situation, and instead of peculiar, I could even call it inconsistent. So this is the question that we need to answer. And let me explain you why it looks like we have found something inconsistent with the theories that we are working with. And so this starts in the following way. So in the previous chapter, we saw, as we have, as I have reminded you, that Rabi oscillations happen when you have the interaction of your atom with a classical field. Okay. In particular, what we saw now put in the context of the light-matter interaction that we have formalized in this chapter, what we have seen is that, or what we saw in there, is that if we make a semi-classical model of light, so of the light-matter interaction, semi-classical model with the electric field equal to just Let me write here, so the polarization X, so it's just the form of the electric field that we have written already several times. Then we have here H bar omega divided epsilon 0 LS. Then we have the mode function sine of K set 0. And now in principle, I should write the A minus A dagger operator. But instead of that, what I write is, because it's a classical field, so I just write some kind of dynamics of the field, which are these ones. And then I write here, let's say, something that we can interpret as the average photon number if we were thinking about a quantum theory in which we measure the photon numbers. But this is just a parametrization of the amplitude of the field, okay? So we have a field that oscillates at frequency omega, okay? So it's a standing wave of the cavity that oscillates at frequency omega, and it has an amplitude that we have normalized in the way that we just define the amplitude by some parameter average n, okay? So the first interesting thing about this is that this is exactly the state that you will obtain if you take your quantum field, okay? So your quantum field, and you just assume that you are in a coherent state with amplitude I square root of n. So this is n and then the square root, and with a minus, if I remember properly. So this state in here is a coherent state. Okay. So in other words, if we just assume that our cavity is in a coherent state that is fixed and it doesn't move, okay? So, I mean, it rotates and so on, but it's not affected by the interaction with the atom. Then we obtain a classical field that has this expression. And using this classical field for the interaction in the semi-classical limit, then we get a Hamiltonian that it's exactly the type of Hamiltonian that we studied in the previous chapter, which is this Rabi, semi-classical Rabi Hamiltonian. So, and here, omega is equal to 2 times the square root of mg, okay? So maybe you start seeing why I parameterize things with n, because this thing here, it's similar to the quantum Rabi frequency that we already defined. So in other words, if we use a semi-classical model with one specific form of the field that we have chosen, but as I told you in the previous chapter, if you just choose any other phase for the field, you will get, instead of sigma x, you will get sigma y, or a linear combination of x and y. This is not very important. It doesn't change the physics, only the math. Then we obtain what we call the semi-classical Rabi Hamiltonian. Okay? Then, in principle, one could think, look, the semi-classical Rabi Hamiltonian predicts that we have Rabi oscillations, just perfectly periodic Rabi oscillations. On the other hand, I find the semi-classical field that I want by taking a coherent state for the light field. Therefore, I would expect, naturally, I would expect that we would expect Rabi oscillations. Let me call them simple Rabi oscillations when we put the initial state of the cavity to be a coherent state. In particular, we choose the coherent state that we wrote above for the field. So again, I remind you, this is a coherent state, not a Fock state. Okay. So we would expect simple Rabi oscillations when we start from a situation in which we have a coherent field interacting with the atom starting in the ground state. But this actually seems very unlikely from our theory, I mean. And this seems unlikely for the following reason, because look at the expression of the probability of being excited. It's a sum over frequencies that are different for different values of n, okay? And then we have the Fock state probability, or the population in the different photon numbers. For a coherent state, that's not picked at one value, that's the Poisson distribution. So this means that we actually have a sum over many frequencies that contribute that are not commensurate, they are different frequencies. And therefore, it seems very unlikely that we will get the simple kind of Rabi oscillation expression for a coherent state when we put in here the Poisson distribution. It just seems very unlikely mathematically. And indeed, we will see that that's not what we get. So we need to understand why. But there is an even deeper problem. I don't know, like it's very weird. So moreover, we have actually found simple Rabi oscillations in the same way as the semi-classical one, but for a state that looks like this, n times the ground state, where now this n is really a Fock state, okay? But this state is highly non-classical. So it's highly a quantum state. It's a Fock state. I mean, it's the state that defines quantization of the electromagnetic field. So then when one gets here, I think one should get completely confused, because on one hand, one expects simple Rabi oscillations when you are in a coherent state, which is a very classical state of light. But what you find is that actually you have simple Rabi oscillations when you are in a highly non-classical state, which is a Fock state. What's going on? So have we failed? Have we tried to define a quantum theory of light that might be incorrect? So hopefully not, because otherwise I have treated you a lot in these weeks of the course. Have we failed in the semi-classical theory? Maybe that semi-classical Rabi oscillation, semi-classical Rabi Hamiltonian, it's really not the right Hamiltonian for light-matter interaction when light is in a coherent state. So what's the issue? So that's what we are going to understand in here, okay? And in particular, this is easy to understand in the following way. So we are going to now analyze the probability of being in the excited state when we start from an initial coherent state. So in particular, this means, as I said, that the coefficients Cn, they follow a Poisson distribution, okay? A Poisson distribution with average in what I call n bar, which is given by this expression here, okay, as we saw in the chapter 2. So this automatically implies that the probability of being excited it's equal, and I will do this working at resonance. Okay, so we just assume that the atom and the field are perfectly resonant. We could do it without it and we would obtain the same kind of physics, but mathematically it's just simple to do this. So let me just consider this special case. And then the probability of being excited is just given by this expression here, 1 minus the cosine term of omega n t divided by 2. And then automatically, this means the following. Of course, the coefficients Cn are normalized. Okay, because the state is normalized. And therefore, we see that this part, this one half of the sum, it's only 1/2. And then we get the other half, that is the sum from n equals 0 to infinity of the Poisson distribution times the cosine of the frequency of each photon. So, yeah. Let me just remind you, because, well, yeah, it's written in there. So this is what we get. And then this is an expression that is simple enough that we can plot with the help of some mathematics program, because this is just a sum. We cannot do the sum analytically, okay? The sum cannot be performed analytically, at least that I am aware of, but we can always do it with a computer. So we can fix one value of the average photon number, okay? N, which I will put 100 for the plot I am going to show you. And then we can perform this sum. Of course, we cannot reach infinity, but we can reach thousands and tens of thousands and whatever you want, up to a value in which the Poisson distribution already falls to 0, okay? And then the sum has converged, okay? So then we can do this numerically. I encourage you to actually do it as well. And then what we get is the following. So I am going to plot. So let me show you here. So I hope you can see it. So what I am plotting here. So forget for a second about the second and the third plots, just focus on the first one. I am plotting here the probability of being excited as a function of time. Of course, time normalized to g, because I remind you that this omega n, so all this factor here, it can be written as 2 times square root of n g t. So you see that g, so the coupling between light and matter, appears only as some kind of normalizing time scale for time, okay? So then we can take gt as the plot parameter, and then plot the probability of being excited as a function of g times t, okay? Then what we get is this beautiful picture here, and what I am doing here is plotting this probability as a function of time only from time 0 to time 5. In the next plot is the same plot, so it's the probability of being excited as a function of time, but instead of 0 to 5, I am plotting from 0 to 65, yeah, okay? And then in the next one, I am plotting from 0 to 300 or 250, okay? So we are kind of zooming out in time. So we are asking, okay, in a short time scale, how is the function? And then on a longer time scale and on an even longer time scale. And why am I doing this? Is very simple, because then you get to see the different kinds of behavior of the function. And in particular, at short time scales, so when the time scale gt is of order 1, okay, what you get are these beautiful oscillations okay, that you can furthermore check if you plot for different values of n, that the distance between the peaks, it's actually 1 over square root of n, okay? And that's precisely the Rabi frequency that you expect for a coherent state, okay? So you expect that in the semi-classical model, the Rabi frequency, it's exactly the one associated to the average of the field, or just the amplitude of the field, okay? So this Rabi frequency actually appears in this initial time scale. However, instead of just simple Rabi oscillations, we have damped Rabi oscillations. So the Rabi oscillations start okay, but with time, they become smaller and smaller until the probability of being excited settles at 0.5, okay, 50-50. So we have 50% probability of being in the ground state, 50 of being in the excited state, okay? On the other hand, and this is an amazing phenomenon that it's a purely quantum mechanical one, if we wait, so it looks like it settles at 0.5, but if we wait long enough, okay, if you just wait long enough, you see how this probability reappears again. I mean, how the function stops being 0.5 and then suddenly starts oscillating again, okay? And then if you see at a longer time scale, you see that these revivals, we call it revival, okay, reappears periodically. And the periodicity goes with a time scale that is proportional to the photon number, to the photon number of the coherent state, okay? So this kind of behavior is what we find when we start from a coherent state initially, and with the atom in the ground state, and we ask what is the probability of being excited. So let me just summarize writing it. So we have Rabi oscillations. So they are there, but they are damped. And in particular, they are damped on a time scale t that goes as 1 over g. And they are damped towards a value that its probability of being excited equal to 1/2, okay? On the other hand, after a time that scales as the square root of the photon number and divided by g, we observe a revival. So what we will call revival. And then we observe a collapse again. Okay? So then I bring your attention to a couple of things. So we will understand in a second where all this comes from. So even though we cannot do this sum analytically, we can understand analytically and from physical arguments where all this physics comes from. And it's a very, very interesting effect. But even just right now, we can already understand a couple of interesting things. And the first interesting thing is that consider what happens for n going to infinity. So we discussed already that when we say that coherent states are the most classical states, what we mean is that we recover the classical statistics of the electromagnetic field when we set a coherent state, so the state of the field to be a coherent state with an infinite number of photons, or very large number of photons. Then, in this situation, something interesting happens, because since this periodicity goes as 1 over square root of n, okay? Then in the time scale of the decay, which the time scale is order 1 over g, okay? We see infinitely many oscillations. So let me write it. So for n equal infinity, then we get infinitely many Rabi cycles. Okay. And this is very important because this is actually telling you, oh, look, if the coupling is small and therefore this time scale is very large, okay? So this time scale in here is large and the field has many photons, in an experiment, you will still see that you have a Rabi oscillation, okay? That if you don't wait a very long time, you will not realize that it is actually decaying, okay? You will just see many oscillations, many oscillations. You will be happy with your experiment. You will say, ah, okay, I see the Rabi oscillations at the right frequency, at the right periodicity, and I'm okay. And moreover, because the time scale between revivals scales as the square root of n, the time that you will have to wait in order to observe this revival goes to infinity. So you should wait much longer than probably you can in the experiment, okay? And we will see this now explicitly, but also the other thing I want to tell you is that these collapses and revivals okay, are deeply rooted in the quantization of light. Okay, so we will see it in a second, like why this is the case. But I just want to tell you before we make a break that whenever you see this kind of behavior of collapses and revivals, that's really a signature of that you have some kind of discreteness and some kind of quantization of your energies in this case. And therefore, this is a purely quantum mechanical effect that is really a smoking gun for quantum mechanics. We already saw one, that is that the Wigner function becomes negative. But now we have also another one, which is these collapses and revivals. This is something that cannot be explained without quantum mechanics. Rabi oscillations, they are semi-classical. We have discussed about them. They can be explained with a classical field. But this particular collapses and revival thing, it can only be explained if you allow the field to be quantized. And we will see in a second why, okay? So maybe we can make a break now, and then when we come back, I will start showing you the physics behind this phenomena. Okay, so let's go back and finish this part of the chapter. So we are trying, or we made the break before trying to explain how all this physics comes about. And what we are going to do is I am going to show you some mathematically with approximations about this, how to perform the sum and so on, how we can find these collapses, okay, and what is the rate of the collapse and so on, so how to explain them. And also from physical arguments, together with some more math, how to find the revivals, make sense of the revivals, both mathematically and physically, and again, of the collapses and the periodicity of this process and so on. Okay, so then let me start with these approximations that we can, or we think that we can do initially, which is the following. So let's find an approximate solution, okay, for the sum. For n much larger than 1, okay? So in particular, when n is much larger than 1, we saw that the Poisson distribution, it's actually a very highly peaked distribution that looks very much just like a Gaussian. So it just looks like some kind of distribution with some average and some width, and it looks symmetric and everything. And so essentially the first approximation that we make is that we approximate the Poisson distribution by a Gaussian distribution. So in general, this always will help because Gaussian distributions are very simple and we know how to deal with them mathematically very efficiently. So this means that we approximate this distribution by a Gaussian that it's picked at a photon number n bar and has a width that it's square root of n. I mean, the width is n, so the variance it's sorry, the variance is n, so the width of the distribution is the square root of n. So if you remember, this is what a Poisson distribution gives you, okay? So essentially what I'm saying is that we do this. We have here the axis of the coefficients Cn, then we have here the axis n, and the Poisson distribution looks just like something that it's 0 at the beginning, and then it's a distribution that has a, so it's centered at n bar and has a width that is square root of n bar, okay? That's the first approximation. And then the second approximation is that, well, if we are going to such high values of n, okay, and then the difference between the probability here and the probability in the next point, in the next n, will be very small. And essentially, this means that we can make an approximation which is replacing the sum by an integral. Okay, in other words, if you want, the sum becomes the definition of the Riemann integral that we are taught since high school, okay, for the particular integral in the limit of n going to infinity of this n going to infinity. So in other words, we get this, that the sum from 0 to infinity, this becomes an integral in the n. Sorry, I should write something like this. From something to infinity. And what's interesting is that because the distribution is picked at n and the width is just the square root of n, which means that the distribution is 0 in all points that are around here, of course, it is 0 even if we extend the variable n to negative values, which doesn't make physical sense, but mathematically, it's okay. Like you can always say, no, my variable is between minus infinity and plus infinity, and that will not change the value of this integration. So this integration, it's the same if we make the integral from 0 to infinity than if we make it from minus infinity to infinity, at least approximately, because the distribution is already 0 here. So the negative values do not contribute to the integral. But we know that if we are doing Gaussian integrals, we need, or it's easier to do integrals from minus infinity to plus infinity. And then this is very useful. And then the last part, it's the following. So in the sum, we have two terms. One is the Poisson distribution that now it's a Gaussian, perfect. But then we have in here the cosine of omega nt. And omega, it's a square root of n, okay? This means that when we write the cosine as exponentials, in total, in here, we will not have the exponential of a quadratic form because we will have a square root of n. And we will have an integration of an exponential of something that goes as n squared and square root of n and so on. That integral is way more complicated than if we just make an approximation for the square root that is the following. The square root of n for very large n, this is approximately equal to the square root of n bar half plus 1 divided the square root of n bar n, okay? In other words, we just do a Taylor expansion of square root of n around the average n, okay? Because we are at such high n's, you see that all these factors, so in particular the linear factor, it's already suppressed by 1 over square root of n, and the quadratic one, it will be even worse. So then we consider square root of n to be just a linear function of n, okay, according to the Taylor series. Then if we do all these approximations, then we obtain a form of the probability of the excited state, which is just 1/2 plus, and then we get 1/4, the integration from -infinity to +infinity of the n, the normalization factor of the Gaussian, and then the exponential, we get first the Gaussian, n minus n bar squared divided to n bar, and then we get here the term of the cosine, and the term of the cosine is I, and then 2 square root n gt, but as I have said, square root of n, we approximated by this, and therefore we get just square root of n plus n divided square root of n gt plus the complex conjugate that comes from the cosine that has the exponential of I plus the exponential of minus I. Then this integration here is completely trivial, and now especially after the exercises, you are perfectly used to this kind of integrals. This is just a Gaussian integral. So it's just the integral of the exponential of a quadratic form. And this integration you can do in the same way that you have done for the exercises, and you will get this very interesting expression that looks like this. Okay? And then here, we are seeing all the physics that we have in this part of the curve. Okay? So we have the Rabi oscillations. We have the Rabi oscillations in particular at the right frequency that we were expecting. Okay? However, these Rabi oscillations are collapsing. And in particular, the collapse rate, so the rate of collapse that we can call gamma shift or gamma collapse, this is just g divided the square root of 2, and we see it here. We have an exponential of minus t squared, okay? With a width of the exponential, which is g square root of 2. And therefore, this means that we recover all these things from just the fact that we have a coherent state of very large photon number. Perfect. So this is really nice because this kind of gives you a reconciliation between what we saw about the Rabi oscillations for a coherent state not being what we were expecting for a classical field. Now we see that they are indeed the same, just with a collapse rate that it's very small compared to the number of Rabi oscillations that you can make, okay? So just like the plot was showing. But here we have some analytics about the collapse rate and the Rabi frequency. But how about the revivals? And the revivals are the difficult part of this story, because you see that from this approximation only, just with this approximation, we actually don't get any revivals. So this probability of being in the excited state, you see that it will collapse to 1/2 for time larger than g over square root of 2. Square root of 2 over g. And then we will never have anything again. Okay, it will just stay at 1/2. So then the collapses and the revivals need to be, so the revivals in particular, they need to come from somewhere else. And that's the physical explanation that I want to give you now and finish with it, which is the physical explanation for the collapses and revivals. So let me proceed in the following way. So first of all, let me just point out that for very large n, as we have seen, only values of n that are in between n minus the square root of the, the average of the distribution minus the square root of that average and n plus the square root of n will contribute to the sum, and in particular, to this kind of term in here. Okay. On the other hand, again, for n very large, note that the frequency, so the smallest frequency possible, which is the one associated to the n equal to the lowest possible n, which we can estimate to be this one, that's actually very close to n plus square root of n. Okay, just imagine if you have 10 to the 4, so n average of n equal to 10 to the 4, then we are talking about a difference of 100, okay, which is very small. So you are saying, what is the ratio between these two frequencies? Okay, between this frequency here and this frequency here will be almost 1. Okay, they will just be slightly different than each other. So, in other words, all the terms in the sum oscillate at similar frequencies. Okay, so this is kind of the initial physical explanation of why initially you see that you have Rabi oscillations at the, let's say, the central frequency, because all the frequencies are almost the same. So everyone starts oscillating in the same way. All the n values, all the photon numbers start oscillating almost at the same rate. However, of course, if you wait long enough, so as time goes by, they will dephase. So they dephase. So you can imagine two frequencies that are very close, they will look like they oscillate at the same frequency initially. But if you wait long enough, in particular the frequency difference, so the time that it's the period difference, you will see how they start, going one ahead of the other. Okay. And this is essentially what will collapse, what creates the collapse, okay? Because then all the frequencies dephase up to the point that eventually they average to 0, because you have a completely random distribution of things oscillating. So they average to 0. And so in particular, eventually getting completely dephased. Okay, and averaging to 0. But this actually gives us a way of predicting just from this argument. So if this argument is true, this means that the collapse rate, it should go as the difference between the higher and smaller frequencies, the largest and the smallest frequencies, which is this one and this one, okay? And this quantity here, again, using a Taylor series expansion of the square roots of, in particular, Taylor series expansion of n around these values and so on, you can write in the following way. So 2g will be equal to, sorry, the frequency at a number n plus the square root of n, that's equal to this quantity here, and the other one is equal to this quantity here. Okay, now expanding this, what you will get, maybe let me do it in a bit more detail. So, oops. So I am sure that you don't miss the steps. So I can pull out this square root of n, and then I get 1 plus 1 divided the square root of n, minus 1 minus 1 divided the square root of n. And now you see that this thing in here is, it can be Taylor series expanded, assuming that this is very small. And this will be expanded as 1 plus 1 divided 2 square root of n, and this one as 1 minus 1 divided 2 square root of n. Okay, and then if we put them together, what we get is a collapse rate that goes as 2g. Okay, so this is the collapse rate. And it's actually a very nice estimation of the real collapse rate that we have just found analytically. So the collapse rate here is g divided by square root of 2. And with this just estimation, this is not a real like mathematical expression, it's just an estimation, it gets order g, it's 2g. So this means that we are on to something. So I think that this really gives you the physical explanation of why we have a collapse. But even more, if it is true that just, you know, the oscillations getting out of phase and back in phase explain collapses and revivals, it should be true that we can find the rephasing times. Or better, that the revivals should coincide with the rephasing time. And what is the rephasing time? This is just the time in which two neighboring frequencies, Rabi frequencies, okay. So essentially, sorry, this is the difference. So essentially, when the time is such that the difference in frequencies with the time, and we will call TR to the revival time, it's 2 pi, some integer, some positive integer, then we will also get a constructive interference, okay? So this means that, okay, they get so out of phase that eventually the one that is faster gets to pick again, you know, from behind the one that is slower. And then when this happens, then essentially, if again we use a Taylor series expansion of these square roots, in particular using that the square root of n plus minus 1, it's equal to the square root of n, and then square root of 1 plus minus 1 divided n. Okay, and this is approximately equal to square root of n, and then 1 plus minus 1 over 2n. Okay, again, this is Taylor series expansion. Then we get a rephasing time, or if you want, revival time, which is approximately pi square root of n divided by g, and then the integer m. And this is actually what we estimate to be the revival time. And we see that it coincides very well. So it's a very good estimation for what we see in the plot. Because I told you that in the plot, what we get is that the revival times are equally spaced in time. Okay, and this is given by the fact that the revival times are proportional to an integer. Okay, but moreover, we have the estimation that the revival time is proportional to the square root of the photon number of the coherent state divided by g. And this is something that you cannot see in the plot, but if you plot this function, if you plot this for different values of n, you will see that actually the distance between them satisfies exactly the ratio that goes with the square root of n, okay? So we get with this estimation the right order of magnitude for the revival time. So this brings me to the end, which is that this is a very quantum mechanical effect, because it's an effect of having a discrete set of oscillators, okay, that are oscillating at incommensurate frequencies. When you have a continuum, this doesn't happen. This, we proved it here. So for the continuous theory, okay, we don't have a rephasing of anything. They just dephase and bye-bye. Nothing can get in phase again. But when you only have a discrete number, for example, 2, of course, they will start dephasing, but at some point, one will pick up with the other, okay? And then when the faster one picks up, then you have a revival again. You have, again, constructive interference, okay? So this is a phenomenon that is really rooted in the fact that frequencies or energies for the electromagnetic field are quantized. And it's something that you cannot explain semi-classically or with a classical theory of the electromagnetic field, okay? So it's one of the smoking guns for quantum mechanics. And this again happens not only for this specific example of one atom interacting with the electromagnetic field and the probability of being excited, this happens absolutely for any quantum system with quantized energy levels. You might have even seen it in quantum mechanics. Some teachers explain collapses and revivals just with the time evolution of the of the hydrogen atom. Okay, that's very common. And if you go to the internet and you check the properties of the hydrogen atom and so on, like Wikipedia or the equivalent in China, you will see that one of the things that they explain in there is collapses and revivals. Okay, which it's something that here appears also very naturally. So in other words, in every quantum system with quantized energy levels, collapses and revivals are one of the smoking guns to make sure that we actually have quantum mechanics on it, okay? So essentially with this, I want to finish the section of this chapter, or half of the chapter, which is about the interaction of light with a single atom. I hope that it's kind of an interesting example, and I think we have seen many interesting effects, and we have discussed many interesting like approximations and so on that are done in quantum optics. And then now we will move in the next part of the chapter to the interaction of light with another completely different type of matter, which is kind of the opposite regime. Here we have a single atom, the definition of a dipole, and so on. Now what we are going to study, and that dipole behaves quantum mechanically, now what we are going to study is the interaction of light with a material, a full material that has a lot of atoms, that it's a condensed matter system, a solid state system that forms a crystal and so on. And these kind of materials have many, many atoms. And we will see how the physics that appear from these materials are also very interesting. And in particular, we will study one type of materials that it's called the electric materials, that probably you have also studied in classical optics. And I will actually review a bit of the classical optics of these materials, and only then I will go to quantum optics and show you how with these materials we can create quantum states of light or interesting states of light like squeezed states and so on.